so we are just resuming this. We were here, so minimum expression is 0, maximum is 1.3 million in this sample wild type 1. 41 is the median, mean is 1646, mod is 0, quartile 1 or Q1 is 8, and Q2 or quartile 2, that is the midpoint, is the same as median, that's 41, right? And Q3 is, my mouse is a little bit off, so I'm clicking here and he's going one step down. Q3 is 253, right? So 75% of the population, or it is 75th percentile or third quartile, right? So in quartile plots, we covered that in theory, that you take the data and you divide it into 4 equal parts. If you divide it into 2 equal parts, we call them as halves or halves. If you divide it into 4 parts, we call them as quartiles. So you have the first quartile, second, third, right? If you convert the same quartile thing into percentile, quartile means out of 4, percentile mean out of 100, right? So this is the first quartile is 25th percentile, this is 50th median, and this is 75th, right? So 25% of the population, or lower 1/4 of the population, is getting 8 reads or below. So for example, these are salaries data, and this is their these are their salaries per hour. So 25% of the population are lower class, 1/4, 1/4 lower of this society segment, or 1/4 lower segment of the society is getting up to $8. Up to 8 means from 0 to 8, right? And the 50% of the population is getting up to $41, right? And 3/4 or 75% is up to 253, starting from 0, right? So up to 253. You can just look into the score or range for each individual class as comparable to previous one. So between Q2 to Q3, the distance is 253 minus 41. So you can get their own ranges, right? Q3 minus Q1 is called as interquartile range, IQR. So that is your exact middle 50% of the population, right? The middle 50% of the population starting from Q1 and ending at Q3 is your middle 50% of the population. So that has a range from 253 to 8 to 253. So you can do it as 253 minus 8, right? Total mapped reads in this sample. So what is the total amount of money or amount of dollars, or the total gene expression values or the numbers we have in this column? So that is, we can get it with the function sum. So sum on all this is the total. So that sum is 9534517. You find it hard to read it in millions, no worries, you can take this number, and million is 1 and then 1k again 6 zeros. So you can take the number and divide it by million, so that is 1 and then 6 zeros. So many of them are here, 5 and then 6, so that is, now this data is converted into millions. So total reads here in this sample are 9.53 millions, right? So this is the overall summary statistics of this sample number 1. Similarly, you can drag this thing to the right and it will give you, and obviously this will shift your reference. This is the reference. So earlier it was C to C and now it becomes D to D. So here it's C to C, right, the column C, and now when you just drag it on the right, it applies to the next column, that is D. Similarly, you can just drag this thing towards your right. Again, the same thing applies there. So that's one beautiful thing which you can get it in Excel. Or you can select this first one and then you do with shift, you select this last one, and now everything in this whole chunk is selected, and you can drag this whole thing on the right. So it will take some time, but it will calculate that summary statistics for you, right? And then you can compare that statistics. But in R, it's just one step, summary, and then you give the file name and everything is calculated. All these things are calculated in just 1-2 seconds. So here it's taking a little bit long because in Excel those functions are applied to each and every row and column, so that's why and then another thing is, in Excel we have to do each and everything while our file is open. So when that file, I mean this is a small file that has 6,000 rows and 8 or 10 columns, so it's not that big, but in real life you might have, like in my analysis in soybean, so I have 200 columns for 200 samples, and there was the 70,000 transcripts for each particular sample. So that was 70,000 multiplied by 200, so that data set was too big. If I open that file in Excel, I was not able to work on any other application, right? So that thing is, you don't need to do that in Linux, you don't need to do that in R, right? So this first part we just calculated. There is one method called as normalization, RPKM, reads per kilobase of the transcripts per, I can just do as summary statistics are just summary, not RPKM. So RPKM is just one normalization method. I will not cover that right now because it will confuse you more. I will do that when we do this DGE testing. Now we come towards this differential gene expression thing. So earlier we processed this file column wise and we can have this summary statistics. Now you have this in front of you. You can see that this sample 1 ranges from 0 to 1.3 million. This goes 0 to 1.6, 0 to 1.4, 0 to 1.6. So some of these samples have high expressions. Overall, like this guy has 9.53, this has 11 million, 10, 10, 11. This seems like 3.8, which is very, very little or less, right? So 3 million reads are here, which is low or less, but comparable to rest of them, the expressions are overall higher. Similarly, the overall distribution is lower here because 0 is minimum and this guy is 0.58 million. 20 is the median here, 660 is the mean here, but for rest of them the means are more. So seems like this sample little bit messed up, or it had a bad day overall. Quartile 3 is 3, 20 and 0, and here it's 41, 48, 53, 68, 48, 67 and 20 here, right? Medians, Q1s are 9, 12 and 13, but here 8, 9 and 10. Seems like the overall expression is higher here and lower on the mutant type, right? So most of the genes, as we can see, are not that affected, but quite a significant number of the genes has been down regulated, right? So this way you can do a comparative, but in R we will make their graphics or pictures. So using those graphics, this analysis will be easier rather than going into those tables, right? So let's move on towards differential gene expression. What is that? It's the expression of the same gene across different treatment conditions. So here are two conditions. One is wild type, one is mutant, right? So it's the expression of gene across different samples. And we know that these samples are grouped. So this group is the wild type group, this group is the mutant group. So if we want to get the average of the expression of this gene 51 35146, so it ranges from B2 to D2, right? Similarly, in mutants, it goes from E2 to G2. So can I get the average of this gene's expression in wild types? Yes, I can. So what I can do is average, and from where to where? You can click just here and then just drag it. Keep the right click pressed and drag it on your right. So that is 582.6667. For mutants, again, what we can do is equal to, and then again average, right? So average, and we click here and drag to the right, right? That's what I can do. The difference between these two, so here the average is 582 reduced to 566. So expression is gone up or down in mutant comparable with wild type. So wild type is your reference or base case. Mutant is your treatment condition. So it will be mutant minus wild type. Okay. So what are your thoughts? The expression is gone up or down in mutants comparable to when compared with the wild type. It is down regulated or up regulated. Down regulated, right? So here we can get that. So this is this number that's there in I2. You simply click in there, minus dash, dash is minus here, this one H2, I2 minus H2, and you press enter. So it's minus 577. So 577 reads less than that. Okay. Uh, this comparison with the actual number sometimes does not make much sense. So we prefer going on to another scale called as fold change. How many folds, how many times the expression is gone up or down. This thing is called as fold change. Like you go to a foreign country, you get a new job, and people won't ask you the actual amount, like how many folds your salary has been increased. If you have, if some company offers you double salary, obviously you will think of moving there, right? Or triple than the previous. So this double, triple, reduced to half, reduced to 1 by 4 is called as fold change, right? So how can you compare the fold change? You can take one thing, you can take one and divide it by other. So here what you're gonna do is you're gonna take this thing on the top, I2 slash, slash means divided by this, so that this will give you a fold change difference, but you are seeing a number very small, a fraction. Why fraction? Because this thing at the top of this equation on before this slash thing was a smaller number, and this thing is called as numerator. Numerator is smaller number, denominator is a big number, so that's why we get a number less than 1. If both terms are equal, numerator versus denominator, your answer is close to 1. More than 1 is where this numerator, the mutant part, is bigger, and wild type denominator is smaller. So it's basically a ratio, right? Ratios are equal to 1 if numerator is equal to denominator, greater than 1 if n bigger than d, less than 1 if n less than d. So numerator and denominator, the top term and the bottom term, right? So what you do in Urdu, for example, in mathematics, this but a this, right? So that thing where you put that slash, or what you call in our language good old days in Urdu, this but a this, right? So that batte ke niche jo hai, that's your denominator, the top term is your numerator, right? But since we see this small number, very small, or fractions, we hate that, so we try to convert that into log scale. So there is this log scale which actually our tools are using. So one of them is log, and then log to the base 2. They are using log to the base 2. So log over k2 comma base is 2, which we are using. So that is the log fold change, or log 2 fold change. So that is, now the answer is minus 6.684. How many fold the expression is gone down, and now the things are in powers of 2. The thing is in log scale, and this log to the base 2 is used. Natural log is not used. In natural log, the things are in powers of 10. I'll come back to this point in a moment, right? So here, let me get back to it, and I want to apply it for all the rows down this column. I can simply go there and take that mouse and hover that mouse, and when this mouse this hovering mouse reaches here, the cross becomes black. I do this double tick, and everything is applied down the column, right? Similarly, I can do it here, right? I can do it here. So actual numbers, and then the right there log to the base 2 thing. I'll show you in a moment what is this log to the base 2 and what is the advantage of doing that. Last but not the least is, now we apply a statistical test. So we realize that the expression is significantly reduced from the average in mean, or average in wild type was 582, and it reduced to 5.6, or something like 583 to 6. So total 577 reads are in terms of the fold change, and this thing is 0.0097254. How many fold this 0.00972? We can say that how many fold the expression has been reduced. By looking into this fraction, it's really hard to estimate. But if you look into this log to the base 2 of this fold change, we can judge that. So this thing is actually 1 divided by 2. 1 divided by 2 raised to power 6.6, or 1 divided by 2 raised to power, let me um, make it simple. So 6.68 is close to 7. So 1 divided by 2 raised to power 7, right? So the expression has been reduced to 1 divided by 2 raised to power 7. What is 2 raised to power 7? That means you can take 2 and multiply it 7 times with itself. So 2 power 7 is क्या बनेगा बताओ? हाँ, 2 दूनी 4 दूनी 8 दूनी 16, 7 दफ़ा लिख के 2 को ज़र्ब दें, या कैलकुलेटर है तो आप करें ज़रा। हाँ करो शाबाश, आप भी करें। Participants, you can also do that. Let me see who brings this real quick. 128. So 128 times reduced. So in order to judge this 128, so it is 1 divided by minus 6 means 1 divided by 2 power plus 6, right? And I just simply reduce this 6.68 to simply round it up to 7. So 1 divided by 2 power 7. So 128 times less, but it is really hard to judge this thing from here, right? 2 in log to the base 2 means 2 power 4. 2 is actually plus 2, na? Right down there, maybe we can see there are some of them whose I think on that side it's really easy to understand. So I can go to data and I can go to log to the base 2 fold change, and I can go from largest to smallest. Okay, so some of them they were not having the good day. We simply ignore them because on one side you have the value, but on other side you have 0. So these are your obviously wrong calls or wrong numbers. We simply remove them. Some of them they are just 0 on both sides. We don't need to keep them, so we simply remove them from our analysis. But just let me pick where we have the ones. Maybe I can just get rid of these folks. Okay. Right, so yeah, you see that some of them they might be giving you the significant results, but it's it's a noise. So maybe we can get rid of these 305 genes and get this one. So this is 2 raised to power 6.6, not negative, it's just a positive number, right? In terms of fold change, it was 97.66, right? So that is 98 times bigger than that. And log to the base 2 scale, maybe if you take 2 and you take it 2 raised to power 6.6, so that is probably close to this number, right? 5.7 is something which is close to 54 or 57 or something like that. Okay, so that is in log to the base 2 scale, right? You can take its anti-log also, and when you do that in the next column you can convert back to this actual number. But the tool or the software reports you this thing, not the actual difference. It does not, I think it gives you the averages and then the log to the fold change, and finally we get the p-value. What is the p-value? So here we throw a statistical test and we see that this is a big change, 97 or 98 folds. The expression is going higher, right? And is it a significant change or not? Number one, it's upregulated, but is it significant or not? For that, we need to decide on the basis of another tag which we need to place with this, and that thing is called as p-value. P-value, probability of finding fold change as big as this by chance is how much? So that's your p-value. So it should be less than 5%. So something whose happening is by chance is less than 5% is a very significant event. What is the probability of rain tonight? You look into your electronic devices and they say 0%, and we look outside and there is a rain, then we thank God more because that event is very, very significant. Okay, it's not that normal, right? So here, what is the probability of seeing this thing, this fold change as high as 98 folds by chance? So for that, we need to apply just one test. But in real life, let me tell you that t-test is not recommended because this RNA sequencing data is not a normal data, because you see this statistical distributions tells us that these numbers are quite weird. It's either not normal, right? So what we're gonna do is we apply another test in R that's called as negative binomial test. Okay, our negative binomial distributions will be applied. It's a binomial problem. RNA-seq is not a normal thing. Microarray data is normal because you get the different shades or colors of the signal, but here either a read will map to the reference or it will not map. Either it will align or it will not align. So one of the two things gonna happen. If a situation like this happens, this problem is not a normal problem. It's a binomial problem. Boy or a girl, binomial. Smoker or non-smoker, obviously binomial, right? Patient or healthy, alive or dead, right? So all are binomial problem. Whether you catch your plane or whether you miss it, a binomial thing. Okay. Right, so one of the two things is you win or lose binomial. So t dot test, just for instance, just to tell you the value, this p-value thing, and how do this differential gene expression thing happens. In real life, we don't rely on Excel, we don't use Excel, we don't use it at all, right? But later on, while you are making your tables and presenting your thesis, obviously you can use that. But rather than going straight away to R, we just took a detour to make these terms clearer to you. These quartile things and these fold change and log fold change and the p-values, and then when we switch gears towards R, I think things will be really easy for you, or maybe you can understand it better, right? Okay, so first distribution is these three numbers. So we are comparing these three numbers. That's one distribution, right? Versus other one. I'm sorry. So we are here. T-test from here to here, comma, right? And then from here to here, comma. And what we can do is he's giving us mashwara, so we can just look into what t-test does and how this thing is applied. I think net messes up, so no worries. So you can open up, you can just click this thing and I think it's coming, and he can teach you this t-test returns the probability associated with student t-test. Use t-test to determine whether two samples are likely to have come from the same two underlying populations. Why it's called as student t-test? Anyone knows the reasons? So t-test, array 1, array 2, comma, tails and type. Array 1, the first data set. Array 2, second one, tails, whether it's one tail, two tailed, or one tail to the right or one tail to the left. Differential gene expression problem is two-tailed because gene can be upregulated or gene can be downregulated. You can have big numbers on this side or on this side, or it could be other way around. So it's two-sided. Sometimes we are only interested in one side, that this drug or medicine decreases the expression of or those genes which are dangerous. So here we are looking for only one tail to the left, right? Maybe in another experiment we are looking for a drug or some additive, or some food supplement that increases the muscle growth. So over there we are looking into one tail test and maybe one tail to the right, because this distribution, which when you draw, it has two sides or tails, right? So this gene expression problem is a two-tailed problem. And then within that you have different versions of t-test. One is paired, one is two sample with equal variance, one is two sample with unequal variance. We covered that in our data analysis course. Here we don't need to go much into the statistics. We only need this tag, that is this p-value. So what we can do is two-tailed distribution. We press 2 here, and then comma ke baad he's asking whether they are, paired is when you have the same plant and you are doing this thing 3 times before applying a treatment and after applying a treatment. So everything is paired. Here we have 6 different individual pots or different plants, or maybe we have 6 different humans, 3 from the control group and 3 from the cancer group, or maybe these are the rats, we gave them some treatment, or for some of them we did not give any treatment, or placebo has been applied. So in that case, it can be anything. All right. So what we can do is to sample equal or unequal. Just check it and he will give you a p-value. So this p-value is 0.017. So 0.01 is 1%. 0.05 is the limit. So obviously it's less than 0.05. And you can apply it to the ones which are down the column or down the row, right? All rows. And then we can reach till the end. And we can see how many genes are differentially expressed. Maybe I can just simply reduce their width and just teach you some filtering in Excel, right? So in Excel, you can go here, filter, and you can go to p-value, and you can go with number filters, equal to, not equal to, less than, for example 0.05. so less than 0.05 honi chahiye p value, right? So these are my significant genes. So these are how many? So we see, I think they should be yeah, here I'm not getting their actual numbers. I can simply copy from here and paste to another. I just do paste special, right? And paste special is this. So these are the ones which are significant genes. I just brought them to the next sheet, and I realized that they are how many? They should be, I think, 300 something. कितने निकलते थे ये? 300. हाँ, something like that. So हमने वो तो the ones with नहीं वो भी ठीक है, लेकिन I think ये Excel का filter उनके लिए अच्छा रहेगा. They can use for their analysis. 300 something थे कुछ, right? So yeah, so 336. अच्छा, you can also go here and see in 336 में how many of them are upregulated. So here again we can filter greater than 1 करेंगे, log fold chain greater than 1, so these are your upregulated ones, right? So these are the ones which are upregulated, okay? Differentially expressed and upregulated, you can sort them. Similarly, you can have them, or you can go here and see the ones which are up till this point. These are the ones which are upregulated, and as soon as this number starts going down, right? So from here onwards, so 63 are upregulated, and these ones, the remaining ones are the ones which are downregulated. How would you know these are up or downregulated? You will look into this column, log 2 fold chain. How would you know they are differentially expressed? You will look into this column, the p-value column, right? And you have the individual counts, and you can see which genes are differentially expressed or which genes are not expressed, right? So I guess this how we can do that. We just used Excel to teach you some functionalities in Microsoft Excel. Some of you might have find them interesting, or they are new to them. You can do a lot in Microsoft Excel, but we will actually do this analysis in R. That's due next week. So before you come to next week, you can have installed R on your laptops. If not, no issues. We can do that in 5 to 10 minutes. That's really a small software which you can, yeah, you can share the videos. Anyways, thank you so much. So any questions, concerns, or queries, let me know. I hope you might have enjoyed today's session. If not, my apologies for that, but if yes, yeah, cheers. So over to you.
Recording.
Any questions? Recording क्या करनी है? वो
Off
करनी
कर
है.
देना.
Off कर दूं? Why don't you take the recording and cut it